Today's lesson is looking at volume and surface area with some somewhat more complex calculations than just plugging in and figuring them out. So last time we had looked at the cylinder, which was just a plug it in and figure out your total value. But we can have questions where we don't have all the information we need directly. We might have to calculate a few things, or we may have questions that are composite figures. So the second question here, where we have this prism, if we look at this prism, it's got a triangular base, and we've got a side thing of the triangle showing us that it's an isosceles triangle. That's what the lines here mean. That has this long side here being 10 centimeters, the triangle height being 5 centimeters, and we don't know these other two sides. So if we look at the formulas for volume and area, volume of a prism is that capital B base, which remember means the area of the base, times the height of the figure. And the area is 2 times that area of the base plus the perimeter times the height. So we need to know the area of this triangle because it's the base, but we don't have that given to us. We also need to know the perimeter of this triangle, and we only know one side and the height, which does not give us the perimeter. So we're going to have to do some calculations to figure out the sides. So if that makes sense and you think, hey, I can do this, pause and try it on your own. If you're like, no, I need to watch this one through, definitely watch it through, but do pause and wherever you need to. So the area of the triangle, remember our formula for the area of a triangle is 1/2 base height. That's the little b base. So the little b just means the length of our side that's perpendicular to the height. So that's fairly straightforward to calculate. That one is a matter of plugging those into the formula and getting our overall result. Don't forget to watch your units. So centimeters times centimeters gives us centimeters squared. The sides is a little trickier. If we look though, that height, remember, comes down at a right angle. So, and since this is an isosceles triangle, it cuts the triangle in half. So if we look at just half the triangle, we know that height is still 5 centimeters. Now the whole bottom was 10 centimeters. We've cut it in half. So now we've got 5 centimeters here, 5 centimeters here, and it's a right triangle. So we can use Pythagoras' theorem to find that hypotenuse, or C. So 5 squared times 5 squared is 25 each, or 50 together. So if we want to know C by itself, it's going to be the square root of 50. So this allows us to figure out that perimeter, because remember perimeter is the distance around, so now we can go 10 centimeters plus each of those two isosceles sides, those two equal sides. So 10 centimeters plus root 50 centimeters plus root 50 centimeters. And you can keep that value as a decimal equivalent in your calculator. Make sure you are keeping as many decimals as possible. Or just keep all the root 50 as you're doing the calculation. So now that we've done these two things, found the area of the base and the perimeter, we have enough information to plug it into our formulas. So volume, area of the base times the height, we can just plug that in. Centimeters squared times centimeters gives us centimeters cubed. This question did ask us to round everything to the nearest tenth, or 1 decimal. So we've got that. So the area, again, now we have the base, we have the perimeter, we can plug that in, do the calculation, and it works out to 532.8 centimeters squared. Notice the units here, we're going to have centimeters squared for our capital B base. Perimeter is going to be in centimeters, although I didn't show them all, I should have. And the height is in centimeters, so centimeters times centimeters is going to give us 7 meters squared, which is why we can add them. They have the same unit. So that was a single shape, but somewhat more complex because we needed those 2 extra pieces, the area of the base and the perimeter of the base. We can also have questions like this one, where we have a more complex figure, either because it's 2 figures together, or there's a hole cut out of it, or some other thing. So in this case, and this is definitely not to scale, in case you're looking at how thick that is versus the total thickness, the outside diameter is 5.32 meters, right? So that's all the way from one edge across to the other edge, and the thickness is only 0.45. So the reason I didn't draw that one to scale is it is really hard to draw things on Word, and trying to get that to be just a narrow little thing was kind of difficult. Regardless on that, this question is being asked what volume is the concrete going to be in this tube. So we know for a cylinder, which this is, our volume is pi r squared h. But we have, if we took the outer volume, well, that would include that hollow part in the middle. So we need to take the outer volume and subtract the hollow piece in the middle. So we plug in our values for the outer volume. Now there's a little piece here that's a little tricky in terms of those radiuses that we have. So for the first one, we're given the diameter is 5.32. So quick reminder that diameter is twice the radius. So when we want to figure that out, r is going to equal the diameter divided by 2. So for the outer cylinder, that's going to be 5.32 meters divided by 2. So that's where the 2.66 meters came from. For the inner one, well, that's a little trickier because our inner radius we are not told that area, that diameter, but we are told how thick the tube is. So if we take our other diameter, our other radius, 2.66, and we subtract that thickness, we get the inner radius. So that's where the 2.21 came from. So since we're talking about the radius, we do only need to subtract that thickness once, even though we have some on this side and some on that side. Radius is only looking at a half, right? Not looking all the way across. So that's where the inner radius is coming from. Here, let's make this match the part that it is calculating with. That is not what I want to do. Okay, that works. So we calculate the outer one, we calculate the inner one, and then we know the volume of the concrete is subtract the difference between the two. Now you'll notice I kept extra digits on my intermediate steps, and you definitely want to do that because it could affect your rounding in the end. Also, if I had only kept 3 significant figures here, and then I subtracted, I would be down to 2 significant figures. So always keep as many digits as you can so that when you get to the end, you can round correctly. So this next one again, I would encourage you to pause and try it on your own if you can. There's 2 parts to this question: volume that the grain bin can hold, and area that we take to make the sheet metal that goes around it. So if we look at this, we're given the radius and we're given the slant height of the cone. We're given the height of the cylinder, but since the cylinder and the cone are meeting up exactly, the radius of the cone is also the radius of the cylinder. Now what we're not given is the height of the cone. Remember, slant height is going down at this angle. Height is going straight up and down. So when we have these values, if we look at our formula, and I see I did not put in the formula, so let's start with that. So our formula for that is in fact pi. Gotta find my symbol for pi. There it is. R squared times the height. So for the cylinder, we can do that whole thing because we have R and we have height. But if we look at the cone, we do not have all the information we need for the cone formula because we need R and height for that one as well. We have R, but we don't have height. So remember, this makes a right angle triangle, so we can say r squared plus height squared equals slant height squared, and solve that for the height. Once we have the height, then we can plug that into the cone formula to figure out the volume of the cone. And notice it's important to label these things pretty clearly because I'm calculating various volumes, various heights, so it needs to be clear which heights we're talking about, which objects we're talking about. So when I'm talking about volume of the cylinder, I'm using height of the cylinder. When I'm talking about volume of the cone, I'm using height of the cone. So those two heights are going to be different. So total volume, again, best to keep all your digits. I put a note here if you rounded early on these first ones, this one ends up having a slightly different answer. So there is a little bit of wiggle room on these questions, but as much as possible you want to keep as many digits as possible. So the area is a little tricky because we have to mentally envision, well, what is actually going to be metal here? So we're told include a bottom. But if you think about what's going on with this, we have sheeting that goes around the outside, we have a bottom, we have the cone on top, but this circle that's in between the cone and the cylinder is not going to be a piece of metal sheeting. It's hollow in there. So if we look at our total area, we need the bottom, we need the sides of the cylinder, and we need the sides of the cone, but that's it. So we don't need that top piece for either the cylinder or the bottom piece for the cone. So when we look at those three things, well, that bottom is just a circle, so it's going to be pi r squared. The sides of the cylinder, remember that's our lateral surface area, so that's 2 pi r h. Likewise for the cone, we're only looking at our lateral surface area, so that's pi r s. So we've calculated that height of the cone, we have the slant height of the cone, we have the height of the cylinder. So again, it would be a good idea on this formula. I'm actually going to put a little subscript here so that we can make sure we're referring to the right heights and the right radius, although the radius is the same for both of them in this case. So when we do that calculation, right, we're talking about the radius of the cylinder, the height of the cylinder, radius of the cone, slant height of the cone. And again, keeping as many digits as possible wherever possible. Your calculator should have a pi button. You might have to look around for it a little bit. It might be a second function, but you can keep pi with all its digits. You don't need to round it to 3.14 because you have a button on your calculator that'll calculate pi for you. So when we add this all up, we get, now what does it say, to the nearest meter squared. So rounding that off, 403 meters squared. And again, watch your units on these. Our volume are going to have cubic units. Our areas are going to have square units. So the big thing about these questions is label your work super clearly. Make it so that someone else can follow along. Use subscripts if you need them. Or sometimes I'll have students do their work where they say cylinder and they put everything for the cylinder in one box. And they do all the calculations that have to do with the cylinder in that box. And then they'll make a box for the cone and do the calculations there. But do something to make it clear which parts you're calculating at each point so that when you go back and you're trying to put things together, you can actually put those things together. So that would be some examples on a little bit more involved volume and area calculations. Your textbook has a whole section where they've got these composite figures, so definitely go practice them. There's also some additional problems on your worksheet with answers at the bottom of that page, so lots of practice.